answer is yes for a dumb reason.
So
you embed the surface into Rn, and then you embed into Rn plus 1 with the divide. So you have the embedding, you know, B from manifold into R again, and then F from into R, and then you take B cross F.
You're like grab it or something.
Rn, yeah, well, R plus R. P of comma F of T, right? And because this is an embedding, that would be an embedding too, and then you project on.
But then you're projecting onto a curve. Write down the formula again.
Okay, so well, no, let's see. So this is M. Oh, let's see. I think I'm wrong. So this is P goes to D of P, comma F of P. All right, and then I post-compose that with projection onto the R vector, right? So then I project R, and that is goes to. And of course, you don't, you know, the theorem you're using is any compact manifold. So it's a high dimensional Euclidean space.
So can you not necessarily do it in the same codimension?
Yeah, so I mean, a more natural question would be: is every Morse function on a surface? It's like very concrete. Every Morse function on a surface comes from embedding in R.
Right.
Yeah.
That's what I was thinking. Yeah. And then sort of as a follow-up, if that's true, is it true that sort of homotopy of the Morse function can correspond to like isotopy of the surface?
Yeah.
So like, can I always isotop? If I have homotopic Morse functions on some fixed surface,
Can you isotop
the two embeddings?
That I don't think, and I don't know the answer to that question either. My suspicion, isotop in R3, I think the example I asked, the homework question I gave last time, I don't think you can realize that by
That's where this came up, thinking about it.
Right. I don't think you can do it by
But you might be able to do it by immersions, though. I mean,
that's right, good question. Immersions, you may allow immersions, it's, just add those questions to the homework.
Well, I wasn't sure. I mean, I had no sense of
I mean, I thought about exactly the same question. I don't know the answer. Everyone understand the question? No? Yes? So I don't know. Here, go ahead. It's possible that yeah, it's good. I mean, maybe you might be able to come up with some weird example where you know some level set is knotted and some other level set is not knotted, and so if there was an isotopy, then it would be taking level sets to level sets. I'm not sure, but that's not quite right because you know through the isotopy level sets may go to singular level sets and pinch and so on. So, but I would somehow think you might be able to use that to get an abstraction. Okay, so I wanted to talk a little bit about the homework problems and then go back to dimension 4. At least we have, I mean, Eric, do you want to explain what you did with that? I mean, Eric has a computer solution to drawing what I've now called the surf graphic for a one-parameter family of Morse functions coming from projecting this circle to various different directions. And do you want to just explain what you did there? And just use that piece of paper.
That's what it looks like. So the idea for using a computer to do this is that instead of first picking a Morse function and then asking where it has critical points, I want to pick a point on the manifold and ask which Morse functions it will be a critical point of. And so, since we've got this special case where our Morse functions are just projections onto unit vectors, I can look at the tangent line here and take it perpendicular. So I guess you just call it the normal to this curve. Call this V. And suppose that you've normalized it. So the Morse function is literally just projection onto this vector. And it's the only Morse function, well, projection onto V or projection onto minus V are the only Morse functions in our family that this would be a critical point of. And so we can actually get a map from M into our space of Morse functions across R. So in this case, it's S1 across R. Does that make sense? I'm explaining myself well. And it turns out that this map is actually really easy. The critical value is just projecting onto this vector, and it ends up being like just a dot product of this point considered as a vector dotted with V. That's all the map is. And so you can just plug that into Sage and have it make plots for you. And you can do the same thing for a surface in R3, I guess. Any n-manifold embedded in Rn+1. And so if we had this instead, then it would be exactly this, but it would be like a surface of revolution. So if I wrap this thing up, so instead of, I've unwrapped my S1 on this x-axis. So if I took this plot and kind of joined the ends into this annulus, I would get it would look something like this. That would be just, say, the top one here. And so you can imagine kind of rotating this curve around, and you get another surface, but it's like in the parameter space of the Morse functions crossed with the critical values. So for this case, that's a way to get the computer to, well, it's just a way to really explicitly define this graph.
So like in your picture here, if that's sort of like outer portion of that curve in the circle there.
This?
Yeah, that would be like either like level 0 or level 1.
Oh,
or
index. The index, right?
Right.
Those are index 1, right? The one you drawn. Index 1. You've only drawn, now you've only drawn half of the picture.
Yeah.
In fact, I mean, I think you should say that you get two maps from M to S1 cross R. You get an outward one and an inward one, right? Depending on whether it's min or a max, right?
Yeah.
Okay. And then you put those two together.
So the index 1 are like the small curves of like the X and shape.
This should be index 1 here, right? This should be index 1 going out, right? And then this is the maximum.
Oh, so, okay, we're not dealing with the surface here. You're just dealing with the
That's right, yeah, okay, that's right. If it was surface, then it's another index is more complicated, but this would be index 1 and this would be index 0.
So what about, so it seems like the points that could show up, it seems like if you pick some points, like in particular these points, maybe this is what you said, which wasn't following, like one of these points on this sort of equator thing, like those are going to create index 1 critical points for some rotation, right?
Where's that point? Or are you talking about, you're trying to jump to you're talking about a two-dimensional case now, the surface?
Oh, okay. So
but before you get to the surface, I was going to ask, what does this point correspond to here?
It's not a Morse function for that.
Yeah, but what is it? What kind of a point on this surface?
The x cubed.
Yeah, it's like inflection points, right? So somehow there's these inflection points. So somehow from here to here, that's this much, right? And then it doubles back because it turns the other way, right? And it goes this way, and then these become minimum in this section, right? And it becomes maximum again. So what, go ahead.
I'm sorry, okay, so maybe I think maybe wasn't actually following what I thought it was. So this is, you're just thinking of this as a curve, and you're rotating it in the plane of the board?
In R3, just make this the z-axis and just spin it, and it becomes something in S2 cross R.
Okay.
Eric's claim is that if you now take the surface of revolution obtained by rotating this curve in R, in
Right.
R2 into R3,
Right.
then the two-dimensional graphic you get as the in S2 cross R is taking this thing in S1 cross R. It's
No, when you do the surface of revolutions, those degenerate critical points that we had, are those still degenerate, like in the surface?
The ones where it's not Morse.
Yeah.
Yeah, I think so.
It looks like you get
S1 where it's
circles worth of non-Morse
Right.
degenerate ways, right?
But like, it wasn't clear to me that they were actually degenerate on the surface.
And so if you rotate this,
'Cause
right, like you're saying, if you take this inflection point here
Mhm.
and you're projecting this direction,
Well, because if you take like the x cubed, like,
so sort of the local model is something like x cubed plus y squared,
Right.
yeah,
or plus or minus y squared or something like that. Right? And you're saying, is that not necessarily actually degenerate?
right.
I mean, you can draw a picture of that. You can draw x cubed and the x squared in the coefficient place.
Right.
Okay, so why are you wondering if that's not degenerate? If you compute the hash,
Yeah, that's what I was just thinking.
it'll have, it'll have
Zero.
a zero in one direction, right? Like one.
Oh, yeah.
Right, because it'll have an x cubed term, which will still have an x on the left over to take the second derivative. And the y squared will give you a one, right? Okay, so we should, did anyone, there's, the way I originally thought of doing it was much more hands-on, and I think it's not, this is a fancy way to do it, right? But, you can also just sort of spin, right, and see what happens. And at a certain point, you just see a pair develop below, so I think a lot of people probably managed to do that, right? You should get exactly this picture. Well, this picture doubled, right? It's the same. There's also something special about if you make this symmetric enough that you'll have this and exactly the same time on the Earth below, right? If you made a little bit less special, then the Earths would happen slightly different times. Any other questions on this? I asked you for the genus one, but you can defer that.
So I'm still, I can't tell if I'm just super confused, but this is a good question. So, it seems like if you draw that thing on its side, right, then you're going to have index 1 critical points.
That's right.
Right? So like where
Oh, I see.
where are
Okay, so let's try to draw this fun thing, right? So I've got let's
you can leave it genus 0.
Right, we leave it genus 0. Why did I? Whenever I draw that, I put together. We leave it genus 0. And but so then we should have
Close.
index 0. So we should have 0, 0, 1, 1, 2, 2, right? Okay, so when we spin this thing around, we're going to have on the inside of the same thing. So we spin that around. And this. But at any given point, somehow locally, here's this circle of critical points here. And we're only drawing half the graphic. And so, at any given, if you look at a particular direction, right, you could just think about, there's always, embedded in this 2-parameter family of functions are lots of 1-parameter families. So when you go from here to here, right, you see a single index 2 critical point, and then you see a birth of a pair of critical points. And when it's a birth, you know they have to be successive index, right? And so and we know that this one eventually becomes index 2. So that means this has to be index 1. That's one way to think about it. But of course, you can also think about what's happening directly in the surface, right? And this is, you have this point moving further and further here, and then confusing. But so one question is that this point doesn't get sucked into this critical point as you spin. A new pair of critical points are born, right? Which are somewhere, all right, so the new pair of critical points are somewhere near here, right? Those are born first, I think, right? And so then you get a little pair of critical points there, one of which is index 2 and one of which is index 1. And then these two move together and cancel. That's the other thing to notice about this phenomenon, right? You have 2 critical points born, and then one of these is born cancels the other one that used to be there, and this one persists.
Yeah, because that makes sense. So as you spin it, you're going to create the bottom thing is going to create a max, a
Right,
rental max.
right.
And
So
you're saying so it has to be the case that that happens at the same time you get a hyperbolic.
Yeah. I mean, so this is your index. This is moving this way, but simultaneously, suddenly, at this point, a pair are born, and this one is this one is slightly bowed that way. This one is slightly bowed that way. So this is
They spread apart.
that's not, and then they spread apart, and then this comes and joins that.
So whenever you can write F like that,
That's degenerate.
and I guess that's why they're called the singularities when you can write it like that.
Well, this is what's happening at the moment, right? And then that's why it's a birth death singularity.
It's
Then
like afterwards.
if you put this and the parameter t in there plus tx, right? Then or minus tx, when minus tx and the t is negative, you have no singularities, but t is positive.
Is it always the case, or is there an easy way to see that, like, critical points of consecutive index are the only ones that can like cancel and be birthed?
I don't have the answer. I'm not big fan. And I mean, there are 2 ways to address the question. One is generic. Is that the only thing that happens? The other is, could you concoct up some really bizarre function that generically doesn't happen, but magically just makes it therefore? And I think I have a topological reason, but I don't think about it carefully.
So when the 2 lines intersect, right, that sort of implies that they're at the same height, and that would be sort of you get a completely symmetric picture.
Yeah, that's right. That implies that at that point, that should be exactly the time when you're projecting this direction. Because then you've got these 2 points are exactly the same height. And then when you spin more, right, then this one is higher and that one's lower. Right, when you're projecting this direction, this one's higher and that one's lower. Right? And then as you keep turning, then they're the same height.
And then when we were to add the double, we would be picking up the 2 zeros and the other critical 1 point. Because here we've got the I guess.
What do you mean with the, right. We on the inside, you then have this other thing happening. Right. And so then this, that's just, so this is index, this is going on outwards, this is index 2, that's index 0, right? In this direction, say here, this is 2, that's index, that's 0, and we know that this is 0, and this is 1, and it's a 1, and this is a 1, and 2, 2. By the way, there's another picture. So this phenomenon where you have critical points doing this, right, it appears in singularity theory. And it's not, well, actually, there is a something that I hope will show up in the homogeneous case, or I'm trying to figure out how to make it show up, is where you see in a two-parameter family of Morse functions, you see this this little triangle here gets smaller and smaller and smaller, and then disappear. Okay, and this is a kind of singularity that arises in two-parameter families of functions known as the swallowtail. And I forget the exact formula for it, but you can, anyway, there's it's got two parameters, so there's a formula for it, just as I have here, x cubed plus tx. There's a formula that has an s and a t, and it's a degree 4 polynomial. But I'll just there's a sort of easy picture of what's going on here that sort of arises out of this picture, but you can sort of just a purely one-dimensional picture of this this story here is if you take so I'm going to draw embeddings of just a one manifold into R2 and projections. So over on the left I have something like that, so that's a maximum. And then as I move along, somewhere I have a birth of a 1, 0, 1 pair, so I would have something like this. Right? That's a birth of a little pair. And now this one jumps up. That's where they cross, right? And then you keep going, and this one drops down and gets small, and then cancels with that, like this again. And you can see why it should be a degree 4 polynomial, right? Because you've got 3 critical points, right? So there's some degree 4 polynomial, I can't remember exactly, which has, with 2 parameters s and t, so that when various points in s and t space, you have this picture. Well, we will be talking about this stuff much more carefully later anyway. Okay, so anyone have any? Actually, let's talk about the homogeneous case later, and let's talk about the question about connecting metrics that are adapted to functions to later. Let's say that, and let me go back to 4 manifolds. So we were just talking about 4 manifolds, building them to handle instructions of 4 manifolds. As I sort of emphasize, with 3 manifolds, I emphasize the difference between Hegardt splitting and Hegardt diagram. Hegardt splitting is you got the 3 manifold given to you and you break it up into pieces. A Hegardt diagram is like instructions to build a 3 manifold, and they're more or less the same, but sometimes logically you want to be careful about what you're talking about. Instructions to build something or ways to decompose something you already know. And so I'm going to think about these as instructions to build a 4 manifold for a moment. And so we said, well, okay, I draw the 0 handle. I don't draw it, I just draw the boundary of the 0 handle, which is R3 infinity, and I just draw R3. Okay, so there it is. And then I draw 1 handles are attached. So these are B1 cross B3s attached along embedding of S0 cross B3, which is just a pair of balls. So I just draw a pair of balls. There was a little bit of confusion last time about what I was, remember I'm really drawing a ball, a solid ball, not a sphere. So knottedness is not an issue. If you've heard about knottedness of 2 spheres can be knotted inside 4 manifolds, but that's not the issue here. I'm drawing a ball inside a 3 manifold. So it's a small ball. It's really just a neighborhood of points. And I could have just drawn the points, and again, assuming everything's oriented, I don't have to really do anything. Convention is not to shade these in. If you see these pictures, why they just start looking like a smiley faces. Okay. But it's supposed to be a sphere, which is a bounce ball. And then you draw little dotted lines between them to indicate that these are the feet of a certain 1 handle, and these are the feet of another. Okay, so this would be a 0 handle union to 1 handles. Okay. And now I want to draw 2 handles, and 2 handles are drawn by embeddings of S1 cross B2. 2 handle is B2 cross B2 like that. you can draw lots of solid tori running around. You can draw a solid torus just, it doesn't do any interact with the one handles at all. You can just draw a solid torus like this. Say, there it is. There's no embedding of a solid torus. You could put a dot in one. Solid torus, etc. You could also draw a solid torus that runs over the one handle. So these are all the, you know, I've drawn a picture of a 4-manifold with a single 0 handle, 2 1 handles, and 3 2 handles. Okay. However, the problem is I haven't actually, this picture does not sufficiently encode the isotopy class of these embeddings of S1 across P2s. And the frame. Right. So I want to talk abstractly about what I need to specify an isotopy class of an embedding of S k minus 1 across B n minus k. So the question is how to specify isotopy class of an embedding. And so we step back from this particular dimension and visit the problem in full generality. So we can consider isotopy classes of embeddings of Sk minus 1 B n minus k into some n minus 1 dimensional manifold, which is typically the bound. So your n minus 1 manifold is the boundary of your whatever you've built so far. Maybe it's just a sphere, for example. And so the first observation is, we'd like to the first observation is not every embedding of Sk minus 1 into n minus 1 extends. In general, there may be embeddings that extends to an embedding of Sk minus 1 across Bn minus k into n. And I'll give you the simplest example, and then you'll understand the general issue. The simplest example I'm going to give you is non-orientable, but just this is a fully general setting, but you'll see why. So, e.g., if n equals multi-band, then the S and we try to embed n. So n equals 2. N equals 3. N is 1 dimensional. Equals 2. Right? And then k I want to equal 2. So Sk minus 1 is S1. So I'm playing not every embedding of a circle in the Mobius band extends to an embedding of the circle cross the circle. So take the core, circle the Mobius band. And, well, no matter how small of a neighborhood you take of it, it's not going to be circle cross interval, it's not going to be a cylinder, it's going to be a Mobius band. You can't do it, right? So, so this one does not extend. But of course, if I draw a little circle here, right, then that, so a little circle that bounds the disk does extend. Right? So what's the issue here? The issue is the normal level to the submanifold. Okay? So necessary condition is that the normal bundle, I mean, let's see, so necessary condition for some phi from sk minus 1 to m to extend to say capital phi from sk minus 1 across p and k into m is that the normal bundle, some people say the normal bundle of phi, which is probably technically the best way to say it, is trivial. But really, I just think of this sk minus 1 as just being a submanifold of m. Or no way to say this, let's let k equal phi of sk minus 1. I'm calling it k because I'm thinking of a knot, right? Mean that the normal bundle of k is trivial. If you've forgotten what the normal bundle is, take a metric on your manifold M, and then you look at the tangent bundle of M restricted to k, so that'll be, and then you take those vectors that are perpendicular to the tangent vectors to k, right? And that's a bundle, a sub-bundle of the tangent space of tangent bundle of the manifold over k. And so not all bundles are trivial. It turns out that, let's cases in which it's automatically trivial, first of all. So if, we'll make a little table of values maybe, so let's do n and k, well, maybe write n minus 1 and k minus 1. That's really what we care about here. So if actually, yeah. So first of all, k minus 1 is 0, so we're embedding s zeros in, and this is anything at all, then it's automatically trivial, right? Because there's no any bundles over 0 sphere are trivial. Okay. Then if k equals 1 and n minus 1 is I'm not exhaustive in this situation, right? And then if m is oriented, then if m is oriented or orientable, then any surface is trivial because the only non-trivial interval bundle over S1 is a Mobius span, and so if that embeds in it, it's got to be oriented. So then it's trivial. So that's why when we were attaching two handles to a 3-manifold, to the boundary of a 3-manifold, we didn't have to specify how thick. I just draw the core, I just draw the image, and there's it does stand. Actually, it turns out that if k minus 1 is 1, it doesn't matter what this is, if m is oriented. That's trivial because actually that's the only kinds of bundles over one manifold are the only issue is oriented versus not oriented. For any value of n minus 1, including this case from where n minus 1 is 3, it works. But for example, if I have a 2-manifold embedded in a 4-manifold, S2 embedded in a 4-manifold, anything can happen. So 2 spheres inside 4-manifold may not have trivial normal bundle. That's all I'll say.
It seems like this is almost just a more a fancier way of saying this.
What I was just talking about up there, first, I haven't even gotten to the framing yet. I'm saying before you can talk about a framing, you need to know that the thing has a normal bundle, has a trivial normal bundle.
No, I mean like this. You say a necessary condition for this map to extend is.
Yeah, that's kind of just a fancy way of saying that it extends, right? In some. Well, that's the tubular neighborhood there. Okay. So then, saying that it's a sufficient condition is the tubular neighborhood there, right? So this is actually sufficient by the tubular neighborhood theorem. The tubular neighborhood theorem says that any submanifold has an embedded neighborhood that has a bundle structure, but it's embedded in the manifold, and as a bundle, it is isomorphic to the normal bundle to that manifold. Okay? if that's like a weak point in your education, yeah, I would just again recommend the discussion Kosinski differential manifolds. At least that's where I learned it from. But there are lots of other places. It's a completely standard thing. Kosinski gives you a good reference for that. Okay, but now the real question is what? Okay, suppose it does have a trivial bundle. What do we need to do to specify exactly which extension, which embedding works? And the point is there that, so to nail down, so suppose now that K has a trivial bundle. Nail down the extension of the isotopy. Well, see, how do you see that this is a necessary condition? Well, capital Phi, sk minus 1 cross 0 inside capital Phi has a trivial normal bundle. The trivial normal bundle is precisely sk minus 1 cross the tangent space to these balls in these directions. But this sk minus 1 cross bn minus k has more than just a trivial normal bundle. It has a trivialized normal bundle. Trivialized normal bundle means its normal bundle to sk minus 1 cross 0 comes with a particular identification with a trivial bundle, with the trivial bundle, namely s minus 1 cross bn minus k. So what you need, so if any particular extension of little phi to capital Phi will induce a trivialization of the normal bundle, not just tell you that it is trivial, but give you a trivialization. So you need to specify a trivialization. So anyone questions on the difference between knowing that it's trivial and having a trivialization? We'll do examples. Actually, I mean, maybe the simplest example for that is if I take this is s n equals 1, and then I'm going to k is a pair of points. This is k, right? K is a pair of points. Has a trivial normal bundle, but it actually has 4 different trivializations of its normal bundle. The trivializations are, so trivialization is you have to pick, in other words, think of the trivializations, at each point you have to pick a basis for the normal space, okay? So I could pick this and this, right? I could pick this and that, therefore, so this has 4 different trivializations. Well, let me say 4 different trivializations up to isotopy, because I could also trivialize it by making this longer, right? But up to isotopy trivializations has 4 different ones. And so they correspond, and 2 of those correspond to producing an unoriented manifold, right? And 2 of them would produce oriented manifolds. And so then, yeah, that's an example. Okay. And then, okay, so the final claim is that specifying the trivialization of UK up to isotopy. So an isotopy of trivializations is precisely what you think it is. It's just a trivialization. A good way to think of a trivialization now is at each point in the submanifold, you have a basis of normal vectors, okay? And then that moves varying continuously, right? And that's a trivialization. Isotopy of trivializations would just be a 1-parameter family of trivializations. So, you know, they wiggle and move around, but you don't jump to a different trivialization. So up to isotopy actually specifies the extension, the extension to S k minus 1 cross B minus k. And And I'm not going to prove this. This is a complete, if you follow the proof of the tubular neighborhood theorem carefully, you'll just see. I mean, the proof of the tubular neighborhood theorem starts with a particular, I mean, it takes your bundle structure on the normal bundle and integrates it, or it does an flow outward using the exponential map, remember that, to produce this embedding, right? And so if you have two different, so you can use the trivialization to sort of give you just, if you implement that proof, starting with the trivialization, you will get a particular embedding. And then two different embeddings corresponding to the same trivialization. There's this argument where you sort of, I don't know if you remember this, you take your tubular neighborhood, you want to show the two different tubular neighborhoods then are isomorphic as bundles. So you sort of make one, you make one really, really small until it's inside the other, and then there's this, you straighten things out. It's sort of this subtle argument, but I'm going to just follow the tubular neighborhood theorem. And it'll just follow it exactly, but you just have some extra data that you carry along. And so now, so for example, when you're attaching, I mean, this case actually becomes interesting at some point. If you're attaching, this would be where you're attaching 5-dimensional 3 handles, right, to some, say, the boundary of a 5-dimensional 0 handle. You attach them along 2 spheres inside inside a 4 manifold, right? And they can be interesting or different 2 spheres. And if they have trivial normal bundles, you can think about what kinds of trivializations they can have. And I forget the answer. I think that there's actually only 2. There's just 2 possible trivializations of a trivial normal bundle of a 2-sphere and a 4 manifold. And so it's sort of things in higher dimensions. There's a lot of special cases and different behavior and so on. But we're going to focus now on the case where, on this case here. No, the case 3 and 4. S1 inside 3 manifold. And so first of all, observation is it's always this is oriented. So it always has a normal bundle. Normal bundle. And then what do different trivializations look like? Well, so how to see a trivialization? Of the normal bundle. I've got a knot K. So now K is a knot. It's at a 3 manifold. So for example, let's say it's an unknot. This is K. What I'm supposed to draw is as I go around it, I'm supposed to draw 2 linearly independent vectors. So if I orient the knot, then I can go around in one direction. I just have to draw, if you think about it, you really only have to draw one vector. If you make, say, the agreement that we always want to pick some orientation convention, you just draw one vector. Since the normal plane is 2-dimensional, you just draw one vector, and the other one will, up to isotopy, is determined. Okay? Actually, this should worry you a little bit. It's related to the fact that there are 4 different trivializations, but only 2 ways to attach a 1 handle here, because attaching a 1 handle this way, or attaching a 1 handle this way, for the arrows point out or the arrows point in, those produce different modular manifolds. So there's some kind of like orientation. You can consistently flip all the orientations and not change the different morphism of the manifold. So that's sort of similar to what I'm saying here. Just specify one vector, and then the other one by some orientation convention, right handle or something, is just to the right. So I claim that to see a trivialization, you just have to pick one normal vector. So just draw I would say a vector field along K, normal K. You draw a single one, and then the other one will determine the other part of the frame. And so then this should at least give you the intuition that the issue is how many times they twist around the knot. Okay, and you can then draw. How about just draw the endpoint vector? Of course, this is getting super sloppy, right? Because the vector is not in the endpoint of the vector is not in the manifold. If you really want to be careful, use the exponential map, integrate back down onto the manifold. But everything, again, we can. The whole point of the two-bit neighborhood theorem is you can identify two-bit neighborhoods of submanifolds with their normal values. Okay, so I can draw the endpoint of it, and then I can do it goes around somewhere, and then it goes around some times, and back. Okay, for example. So that would be a picture of a framing, of a framed. So this is now what's called a framed knot. And there are various conventions for drawing pictures of framed knots. Well, one of the nicest ones is just, instead of drawing knots, draw little ribbons. Okay, so once you've got a framed knot, you can draw this little ribbon here. And there are other conventions. What you're tempted to do, right, is just write down a number, which tells you how many times it twists around. And that's more or less correct, except for the fact with three-dimensional issue that figuring out what zero should be is kind of tricky. But one thing you can say, and this is maybe in full generality, is that given a knot K inside three manifold, the framings of K framings a torsion, thank you, that's the word I was looking for, are a Z-torsion? Is that the right grammatical formulation? Torsion for Z. That's a fancy way of saying that it looks just like the integers, except you don't know where zero is. You don't know which one you should call zero in general. But another way to say that if there's a Z action on framings, you can always take one framing and put extra twists in it, right? Put it, 25 extra twists in it. That's well defined. The convention would be that the only convention you need to sort out is what's plus and what's minus, okay? And the convention should be that adding this.
So even with the ribbon-like structure, you still don't know which one to hold in, right?
Yeah, I mean, imagine, for example, the best example to keep in mind is if it actually goes over a one handle, then suddenly, suppose it's in S1 cross S2. Unless you've already S1 cross S2 has its own, can be represented as S1 cross S2 in many different ways. And if you change those by a twisting as you go around the S1 direction, you'll change your framings. So knowing what to call zero is completely, it requires something special in S3, which can be done. But we call this plus one, because this is a right-handed twist. If you go in this direction, you see the red curve is twisting to the right. So adding one to the framing corresponds to just taking a little piece of it and putting that in. That's a well-defined operation. Another way to say it is the difference between two framings is an integer as well. But the upshot is here that if you find a way to draw a framed knot, to specify a knot with a framing, then that will determine how to attach a four-dimensional two-handle. So to indicate vacuum maps for two handles, you need to draw framed knots. I will tell you next time how you actually can just write integers next to the knots. But there's a bunch of, when you're going over one half, it's become particularly complicated. There is actually one other nice way to do it without doing an integer, which is, I forget what this image is. So here's, I just have 1 minute left. So one way is to always draw ribbons, or draw parallel copies of the knots, and that's actually something very useful. Another way is to use what's called the blackboard framing. So this presumes that you're drawing your pictures on a two-dimensional something. Okay? And if you're drawing your pictures on a two-dimensional blackboard, then anytime you draw if I draw a knot like that, then the blackboard framing is you push the knot off itself in the board. So this would be the blackboard framing for that. So how could I possibly put an extra twist using the blackboard framing? So the way you would put an extra twist using the blackboard framing is you would draw the same knot, but you put a little kink in like that, and then if you imagine straightening out this kink, this framing, the white knots are isotopic to each other, really. But these are different framing knots. And so by putting little kinks like that in, you can also, that's another way to keep track of framing. So you could say, I'm always going to, all my pictures, all my framings are going to be blackboard framed. And then in order to indicate different framings, you have to put in different kinks like that. And that sometimes is actually a useful convention as well. And so then if you did this, and then this, then of course that's a +1 and a -1. That's that.
I never realized that was twist and right.
Yeah.
Before.
Yeah.
It's cool.